In this screencast, we're going to take a look at Kepler's three laws of planetary motion. This is required information for the AP Physics C exam and things that you should be prepared to demonstrate a knowledge of during class. Kepler's first law is the law of orbits. So I'm going to write this as Kepler 1. Kepler's first law is often referred to as the law of orbits, and it basically suggests that the orbits of planets are not perfect circles, that they're actually ellipses. It requires us to know a little bit about an ellipse. We're going to have a minor axis, that's the shorter axis. We're going to have a major axis, which is the long one. And we're going to have two focal points. I could call that point F1 and this point F2. Now, to understand a little bit about an ellipse, what that means is that any arbitrary point along the ellipse has a sum of two distances. I'm going to call that distance 1, and this could be distance 2. So if this is D1 and D2, and what that means is that D1 plus D2 is some sort of a constant. It doesn't change. I've actually seen this done with pieces of yarn tacked in at the two focal points, and that actually allows you to draw an ellipse. So let's look at some other point, some other random point. Let's call that point Q. And so we would see that the two distances, even though they've changed, the sum of them have to be the same. And so we could say that D3 plus D4 has to be that same constant that D1 and D2 were. So that's basically the nature of an ellipse. And the law of orbits suggests that planets orbit suns or stars, where the sun is effectively one of the two focal points. What that means is that some satellite, in this case a natural satellite like a planet, is passing through an elliptical orbit and it's not circular, which means technically at times it's closer to the sun and technically at times it's further away from the sun. Now, this is not drawn to scale, especially for planets in our solar system. There are debris from the Oort cloud, comets and asteroids that basically follow very highly eccentric elliptical paths through our solar system. Most of the planets in our solar system follow near circular elliptical paths. They're still technically ellipses. This is not responsible for changes in temperatures and seasons that are cyclical. That is a common misperception that has to do with tilt of the Earth axis. So the law of orbits just establishes the ellipse as the standard orbital path that a planet takes around a star. So that's Kepler's first law. Kepler's second law is the law of areas, and Kepler's second law, I'll write that out, is the law of areas. The basis for the law of areas is conservation of angular momentum. We'll get a little bit into that, into the rotational mechanics unit that we do immediately following this. What you need to know is that it follows equal areas and equal times. So what that means is if that some planet is moving in this direction, that the time it takes to go from A to B establishes this shaded region that I'm kind of coloring in this purple color. So that amount of area has to be equal to the amount of area that it established using a similar method in the same amount of time. So let's say to go from A to B, it's going slightly faster than it takes to go to C to D. It's going slightly slower. So what that means is that those two areas, and now I guess I should shade it in a lighter color of pink. So the area that I've shaded in pink, and I will label now perhaps as area 2, area 2 has to be equal to area 1. As long as it takes the same amount of time to go from A to B as it does from C to D, then the areas swept out during those times along the elliptical path have to be the same. The last one of Kepler's laws is the third law, and this one's called the law of periods. It starts with a statement of near circular orbit. So we're simply going to say that the force of gravity is equal to a centripetal force. And we know that a centripetal force can be written as mv squared over r. The gravitational force can also be substituted for. That's going to be G times m1, m2 over r squared. I have to establish this m as one of the two m's, so let's call it mass 1. So that becomes m1v squared over r. Immediately I can see there are some things that I can do. The mass 1's go away. One of the r's on the left, so I have one r there, cancels the r on the right. And now I have v squared on the right. But since it's moving in a circular path, I can say that speed is equal to distance over time. But in this case, it's the circumference of a circle over the amount of time that it takes to complete that circle, or its period. The circumference of a circle is 2 pi r. So I'll write it as such. This becomes 2 pi r over period. Therefore, if I want to substitute v squared, I can either square that or let me just go ahead and do that right now. V squared becomes 4 pi squared r squared over period squared. And then that expression is going to get substituted in for v squared in the next step. So on the left-hand side, I have g times the mass of object 2. Now object 2 is the sun in this case. Object 1 was the planet. Those two masses canceled out. And I'm going to divide that by r, and on the right-hand side, I get 4 pi squared r squared over period squared. Now, I want to combine some things. I'm going to multiply both sides by r, and when I do that, I get rid of the denominator on the left-hand side, and I get g times the mass of the sun is equal to 4 pi squared r cubed over period squared. So then I'm going to multiply both sides by period squared, and that shows up on the left-hand side. Now I'm going to divide both sides by what I have inside the brackets that I just drew. And so this becomes period squared is equal to 4 pi squared over g times the mass of the sun times r cubed. Look carefully at everything inside the brackets. We can see that this is a constant. That means it's a constant for every planet in the same star or solar system. And so we can see that there is a relationship between the square of the object's period and its distance away from that central object, in this case, the sun. And so the law of periods establishes that relationship. Those are Kepler's 3 laws of motion.